So this video is going to cover section 5.2 in your textbook, which looks at systems, surroundings, and energy transfer. So we started talking about energy and how important it is as a driver of processes in nature. Now, this is pretty abstract kind of stuff, what energy is. And we need to spend a little bit of time looking at kind of the formalism behind talking about energy. So there's going to be some terminology in this section, and we're going to focus at kind of broad, general topics from physics. Later on, we're going to apply all of this, so bear with me, this is all going to make sense eventually, but we need to do some of this formalism so we know how to work and talk about energy in a reliable and coherent way. So that's what we're going to be doing. So here's some terminology related to energy transfer. First, we're going to define something called the system. Now I know this seems silly, but the system is just the part of the universe that is the focus of our study. So oftentimes for us that will be, a chemical reaction. So the reactants and the products that get formed from that chemical reaction. So that will make up our system. So it might be a beaker on a table. We can imagine, though, more complicated systems like a cell or a human body or something like that. There are three types of systems, and we're going to discuss what's different about them in a little bit. So bear with me on this. So three categories of systems: isolated systems, or open systems, or closed systems. So after a system, then we can describe the surroundings. And again, this might seem like a silly distinction, but the surroundings is everything else in the universe that is not part of the system. So there are only these two things in the universe: the system, whatever you define it to be, and the surroundings. And an important item is that there will be a boundary, maybe just one that exists in our mind, between the system and the surroundings, some sort of boundary in between the two. So then the whole universe we presume to be the system plus the surroundings. So everything else that's in the universe then will be the whole thing. Alright, so let's talk about those isolated versus closed versus open systems. So here's some examples of things that approximate these kinds of systems: isolated, closed, and open. Now, in reality, there may not be such a thing as an isolated system or a completely closed system, but we can imagine that they exist and then use them to make predictions based on the physics. So first off, an isolated system is pictured over here. So this would be the thermos bottle right here. So the stuff that makes up the inside of this thermos bottle, that is our system. And it is isolated because a thermos prevents heat from being transferred. So isolation means no heat gets transferred between the system and the surroundings. There's no way for heat to get in, no way for heat to get out. The other thing about an isolated system is that it's closed, so there's no matter that can be exchanged between the system and the surroundings. So no matter transfer between system and surroundings. This is not no heal, this is no heat. There we go. The other thing about this isolated system is that the walls are rigid. So that means that the system can't expand or contract. So in this way, there is no way for the system to interact in any way whatsoever with the surroundings. So it is isolated from the surroundings, hence the name. Now that's in contrast to a closed system. So this closed system, imagine that instead of having our soup in a thermos bottle, that we've got our soup in a bowl, just a ceramic bowl, but we've put some sort of lid on the top so the soup doesn't spill out and the steam doesn't get out. So it is possible for heat to get out through the top or the sides because we would feel that as being warm, but there's no way for the water molecules to get out or for little flies to come in and land in our soup. So there's no matter transfer. There is heat transfer, but no matter. And we might have rigid walls or not. So the system might be able to expand and contract or not. So closed just means that there's no matter exchange between the system and the surroundings. Finally, an open system means that, yes, matter can come in and out. Like we might take our soup and add some crackers to it, or some grated cheese, or some pepper. So matter can come in, matter can come out, the steam can come out, and heat can come out as well. So this would be a completely open system. So oftentimes in the lab, we will have our beakers open to the surroundings. So in principle, they can exchange. Sometimes we might close our reaction up and do it in a closed system, although we have to be careful with those because closed systems, we don't want them to try to expand and therefore explode. Alright, so now let's talk a little bit about some of those in more specific details. So let's talk about heat flow. So I've told you that heat can go into or out of a system. So we say flow, but realize there's no substance here that's flowing. We are transferring energy. So heat is a way of, and we've talked about this a little bit, heat is a way of energy transfer. So heat is one way that we can transfer energy from the system into the surroundings or from the surroundings into the system. So we're going to define an exothermic process as any process where energy as heat goes out of the system. So if heat goes out of the system, so our bowl of soup is cooling off because heat is leaving and going into the surroundings, then we're going to call that an exothermic process. So in physics, we use the lowercase q often to designate heat. So that's our symbol for heat. It means quantity of energy transferred. So there's an amount of heat. And this little less than sign right here means less than 0. So we're going to give that heat a negative sign, so negative sign, whenever that energy is going out of the system. So this is what we call a sign convention. Convention is just something that we all agree on. So we're going to agree from now on that we're going to give heat a negative sign to indicate the direction in which it's going. Is it going into the system or out of the system? So we use a negative sign for out of the system. So the contrast then is an endothermic process. Endo means going in, exo means going out. Those of you that are biologists might know that certain animals have an exoskeleton, so that's a skeleton that's on the outside, right? So we can think about heat going out. So endothermic process. In an endothermic process, energy, as heat in this case, is transferred into the system from the surroundings. So in this case, the surroundings would be heating up our system. So our system is gaining heat from the surroundings. So again, we're going to use Q as our symbol for the quantity of heat, the quantity of energy that is transferred as heat. And in this case, our sign convention is going to be that it's greater than 0 or positive. So we're going to use a positive sign to say when we have heat going into the system. To help keep these straight, here's a little mnemonic that you might like. So, from the system's perspective, the system, just like any of us, likes getting stuff, right? So if heat is going into the system, that's a very positive thing because the system is gaining. So we're going to think about, positive is getting something, right? Somebody gives you a present, that's a positive thing. And so that's going to give positive when the system is gaining heat. So I drew that in the wrong place. So the system is gaining energy as heat. Now if the system is losing heat because heat is going out of the system, well, whenever you lose something, you're sad. So that's a negative thing, right? So I drew some minus signs here and a sad face. So that's a negative thing because heat is going out of the system. I mean, systems don't have feelings, but this is just helping us remember the sign convention, okay? So when you're losing heat, that's negative. When you're gaining heat, yay, that's positive. Okay, so let's look at some specific examples of endothermic and exothermic processes. So in this case, we've got some, let's look at this one first, actually. So we've got some liquid. Let's imagine we've got a droplet of water here. That's our system. So what we're going to do to that droplet of water is we're going to drop it on a hot skillet or a hot plate, and so heat is going to go from the surroundings, that hot plate, into that liquid water droplet. And what's going to happen is that heat is going to boil that liquid droplet and convert it into water vapor, a gas. Okay? So it is heated up and it is gone to vapor. So in that case, energy as heat is going into the system, right? Remember, that's positive, so we give it a positive sign and we call that an endothermic process. Now let's look at the reverse of that process. Here we've got vapor, say on a nice cool day, water vapor in the air, and heat's going to come out of that vapor. So as you start to cool that vapor down, those water molecules will come together and they will condense as liquid droplets, say on the leaves of plants, and that's how we get dew. And so we have taken heat out of the system. So the system loses heat to its surroundings, it's cooled off, and we've reformed the liquid. That would be an exothermic process. So you might not think of condensation as a liquid as an exothermic process, but it is. Heat is going out of that hot vapor into the cooler surroundings. Okay, so we're cooling it off to make the liquid. Notice something interesting here, that if we look at this process in this direction, well, it's just the opposite of this process. Liquid going to vapor is the opposite of going from vapor to liquid. So if it is exothermic in one direction, If you were to reverse the process, that process will be endothermic. And that's an important distinction, that a reverse process will always change sign of the heat going into or out of the system. So let's look at that in more detail with different kinds of phase changes. So this is sort of showing a gas, liquid, and solid, the three phases that we deal with in chemistry. And this one is pictured at the top as sort of the most energetic system. So this is the one where the molecules have the most kinetic energy. Here's less kinetic energy, and so on. So we've given the molecules the most kinetic energy up here. So what we're going to do is imagine that we're taking some of that heat out. So there are several processes that we can do to do that. We can take out a lot of heat, convert that to the solid, the gas to the solid. That process is deposition. Take out some more heat from the gas just to convert it to the liquid. That's that condensation process. Or we could take heat away from the liquid, again, to solidify it or freeze it. So these would all be exothermic processes. So converting the gas into a liquid or the liquid into a solid, those would all be exothermic. Now, you may not think of liquid water going to ice cubes as being an exothermic process, a process that releases heat, just like the burning of fuel or candle releases heat, right? So that's an exothermic process as well. Well, freezing a liquid is an exothermic process because you have to take heat out to make that happen. The converse is true, that adding heat to a solid will melt it, adding heat to a liquid will vaporize it, or adding heat to a solid under the right conditions might convert it all the way into a gas, and that process is called sublimation. So let's look at energy and phase changes at the microscopic level. So here's an ice cube. Now in ice is made of water molecules. So here's some water molecules here. I'll circle one. There's a water molecule. It's made up of an oxygen and 2 hydrogen atoms. And in ice, what happens is these water molecules are held tightly together to each other by something that we'll learn about later called intermolecular forces. In particular, something called a hydrogen bond. So these relatively strong interactions hold these water molecules pretty tightly. As a model, you might imagine that we've got these things held together by Velcro. Now at low temperature, they still have kinetic energy, so they're in fact moving around a little bit. They're rattling around, bumping into each other, but can't really quite overcome their interactions. So imagine shaking this container, they're all connected with Velcro, a little bit, so they're all kind of jiggling about, but not strong enough yet to break the Velcro. So if we add heat, what's going to happen is the solid will melt into a liquid. So here's what liquid water looks like. So we've added enough heat to really increase the kinetic energy of these molecules, and so they're moving really quite quickly back and forth together, and we break those intermolecular interactions. It's as if we've ripped the Velcro off because we're shaking that system so hard. And now the molecules are free to tumble around, although they're still making and breaking connections all the time. So the Velcro sticks and then comes unstuck, and sticks and comes unstuck, but these guys are able to tumble around each other. And that's what the liquid state looks like. Now if we continue to shake our box really, really hard, eventually these molecules might all come apart and fly out of the box, so that there's no chance now that they really come in contact with each other, except only rarely. So the Velcro is completely broken, and these guys are really ripping around, and that would be an example of water vapor. So we've overcome those interactions and really increased the kinetic energy by adding heat. Now we can imagine the reverse. So we're going to cool these guys off. So what we're going to do is slow them down. So we start to remove their kinetic energy. Well, now they can start to bump into each other, and when they bump into each other, there's a greater chance that they're going to stick together. So they stick together, they release some more heat as they form these interactions, and they form liquid water. If we keep removing heat, then eventually they're going to slow down enough, because we keep removing that thermal energy, they slow down enough that they're not moving very much, and they stop breaking all those interactions, and they lock into this structure that gives us solid ice. Again, just to summarize, absorbed heat then is going to increase the kinetic energy of the molecules, and that's what we see when we're going in this direction, right? From solid to liquid to gas. The converse is true, that losing kinetic energy is caused by the release of heat into the surroundings. So as we release heat into the surroundings, these guys are going to cool down, and we're going to form these interactions and go backwards to reform the solid, so from gas to liquid to solid. So let's look at another important concept. It's called internal energy. So we're going to give internal energy the symbol E right here. So what is internal energy? So imagine we've got our system. So our system might be made up of atoms, molecules, electrons, all that stuff, right? That makes up matter. So internal energy then is the sum of all the kinetic energy and all of the potential energy of all components of the system. So for example, a molecule can have different types of motion. The first type is the molecule just moving around through space. We call that translational motion because the molecule gets translated from one location to another. Trans means kind of across, so it's moving across this space. There's also rotational motion, so we can imagine that these molecules are kind of tumbling around their axes. So the molecule is rotated from this position to this position. And as long as it's moving, spinning around, it might be in the same place, but it still has energy of motion. So that would be rotational kinetic energy. There's also vibrational motion. So imagine this water molecule connected like this. We can imagine these hydrogen atoms moving in towards this oxygen atom and back out away from it. So that type of motion involves this bond vibrating. Here's another bond vibration in water. So these atoms, the hydrogen moves in, and this one moves away, and then this one moves away, and this one moves in. So they're just kind of going back and forth like that. So that's a different kind of stretch. So that involves vibrational energy. Now, vibrational energy is energy of motion, but it is also changing the potential energy because as these particles, the hydrogen and the oxygen, move closer or further apart from each other, they're going to change their energy due to position. That is potential energy. So we need to add that in too. Now, in addition to molecules, remember that there are also electrons. So the electrons are moving around the nuclei. So based on the position to the nucleus, they're going to experience a Coulombic attraction potential energy, and also relative to the other electrons, they're going to experience some potential energy. Electrons are also constantly moving, so it's like a swarm of gnats around this molecule. So that gives them kinetic energy. So the electrons are going to have energy. We also have energy in the nucleus that holds all those protons and neutrons together. Also, there's, Einstein says, relativistic energy, E equals mc squared. So simply because an object has mass, rest mass, it has an equivalent amount of energy. So all those energies sum together then to give us the total internal energy of our system. So the energy of our system can change, right? So we're going to represent any change by this Greek letter delta. So delta just represents a change. So this is the capital Greek letter delta. And so when you see delta E, that means, hey, the system's internal energy has changed. And delta will always mean that, oh, you just need to know the final energy. Okay, we're going to subtract from that the initial energy. So delta means final minus initial. Okay. Now, energy is a state function. We've already talked about that. And that's just a fancy word that means it depends only on the state of the system, not on how it got to that state. So we just care about, hey, the system is in some final state, some final set of conditions. What's its energy there? Okay, and it started in some initial state. What was its energy there? Now, in going from the initial to final, it probably went through a whole bunch of other states. We don't care about that. We just care about the initial and the final, and from that we can calculate the change in that internal energy. All right, so this has all been some formalism that we need to think about energy. So we've defined system, we've defined surroundings, we've defined what we mean by internal energy, exothermic and endothermic, and heat going into or out of the system. Let's look at the units on energy. So if we're going to be talking about energy, energy is something that can be measured. Well, we can actually measure energy changes relatively easily, but we're going to assign numbers to energy. We're going to measure energy changes. So one way to measure energy change is in units of calories. This is called an operational definition, and this calorie is also called the thermochemical calorie, and it's given the symbol CAL with a lowercase c. So this is an operational definition because this is the amount of energy, heat energy, that is needed to be added to raise the temperature of 1 gram of water by 1 degree Celsius. So from 15.5 degrees Celsius, from 14.5 degrees Celsius up to 15.5 degrees Celsius. So that's the definition. Whatever amount of energy you have to put in to make that happen, that is 1 calorie of energy. You may have also heard of another kind of calorie that we call the nutritional calorie. So this is the thermochemical calorie. So the nutritional calorie, that's supposed to be an I right there, is usually given the symbol capital C-A-L, and it's called capital C calories. And that is equal to 1,000 of these thermochemical calories. So this is how we measure the energy content of food. So people often care about their calorie intake. So a normal diet, a person might eat 2,000, 2,500 calories a day. Those would be these capital C calories, or each one of these calories is 1,000 thermochemical calories. All right, so you can raise a lot of grams of water by 1 degree C with all the calories that we eat in a typical diet. Well, that's pretty good because you have to heat up your whole body, right? And your whole body is made of water, so we need lots of energy to do what we're doing and just keep our body warm. So the SI unit for energy is the joule, given the symbol capital J, so that's our SI unit. And the SI unit is really what we call a derived unit. So 1 joule is equal to 1 kilogram times meter squared per second squared. And we can see this using our kinetic energy formula. So kinetic energy of a moving particle, a moving mass, would be 1/2 mass times speed u squared. So mass would have units of kilograms, right? Speed would have units of meters per second, and we're going to square that. And that's how we get this derived unit, 1 kilogram times meter squared divided by second squared. Now there's a connection, a conversion factor between calories and joules, and so 4.184 joules is equal to 1 thermochemical calorie. Okay. So if we're doing energy transfer, so heat and work are ways of transferring an amount of energy, and they're going to have the same units. So I use this analogy that energy transfer is kind of like an analogous to a check when you're transferring money. So a check is a way of transferring money into or out of your account. Now, checks are going to have units of dollars, but in fact they are not real money, right? It's not legal tender. It's not an actual dollar. In the same way, heat and work transfer an amount of energy, and so they're going to have the same units of energy, joules or calories, but they are ways of transferring energy in between the system and the surroundings. Okay, now we're ready to get to the real heart of the matter. This is the first law of thermodynamics. So like other laws, this is a summary of our observations of experiment and experience, generalized so that it applies as broadly as possible. So folks thinking about energy and heat and work back in the 19th century proposed this law of nature, sort of a statement of the way things are. And so with regard to energy, we have come to observe that the first law of thermodynamics, we say that is the law of conservation of energy. So energy is conserved. That means not created, not destroyed. So there's no way to create or destroy energy. We can only transfer it from one part of the universe to another. Another way of saying that is that the energy of the universe is constant. So if I were to write the change, delta, in the internal energy of what? I'm going to put a little subscript here, UNIV for the whole universe. Well, so the universe is system plus surroundings, is everything that there is in all of reality. And so we assume that that is like an isolated system because there's nothing beyond the universe. And so the energy change of the universe would be equal to 0. We could also say that the energy change, the internal energy change of any isolated system is also equal to 0. So the energy change of the universe is constant. Delta E universe equals 0. So there's no net energy change in the universe. So energy is not created or destroyed in our universe. Another way of saying that then, energy gained or lost by a system must be equal to the energy lost or gained by the surroundings, right? So we can write, since the universe is system plus surroundings, we can write the change in the energy of the universe, which we know is equal to 0, can be divided up into two parts, right? The change in the internal energy of our system plus the change in the internal energy of the surroundings. So I'll write subscripts SYS for system, SURR for surroundings. So that's going to be the total energy change of the universe, and that has to be equal to 0. So if we solve this for delta E of the system, we get negative delta E of the surroundings. So any energy that's lost or gained by the system has to be correspondingly gained or lost by the surroundings. So if our system gains energy, the surroundings has lost energy. So that's a consequence of this first law of thermodynamics, that energy is conserved and cannot be created or destroyed. So a very important concept that we will use when thinking about chemical reactions. So now we're going to look at how the internal energy can change. So another consequence of the first law, so this statement right here is really another way of writing the first law of thermodynamics. So we've seen a couple of different mathematical equations that both are essentially equivalent to the first law of thermodynamics. So the first law of thermodynamics says, okay, the only two ways that a system can change its energy, so we're here talking about delta E, it's the energy of the system, is through heat and through work. So we're going to imagine that those are the only two ways that the system can change its internal energy, by exchanging heat with the surroundings or doing work on the surroundings or having work done on it by the surroundings. So delta E is the total change in the system's internal energy. Q is going to be our symbol then for heat. We've already talked about that. And W is our symbol then for work. So the total change in the system's energy is due to the heat plus the work. So if we happen to know what these quantities were in joules, we could simply add them together. They might have positive or negative signs, so we would want to be careful to include those signs, and then we would get the total change in the energy of our system. So work, how do we calculate work? Well, work is calculated through an equation from physics that says work is equal to force times the distance over which that force operates. So this is a useful definition for work in physics, but in chemistry we often don't see things moving around quite like that. But what we do sometimes see is our system, maybe if it's a gas, will expand or contract. So expansion or compression is a type of work because you're pushing against the surroundings. So let's imagine that I've got a can here. So I've got a can, and inside that can I'm going to put a little movable piston, a little top. So imagine this little circle that's inside our can can move up or down. Okay? So inside we've got our system, and let's say it's a gas. So we've got a gas inside our system, and sitting on top of this piston, then we've got a weight. So this is some sort of mass. This mass is pushing down. Okay, I'm having problems with my writing here. So this mass is exerting a force due to gravity downwards on this piston. So we say that it's creating a pressure. So this mass is creating a pressure due to this mass pushing down. Okay, now imagine that we heat our gas up. These gas molecules can now be moving around faster. They're going to bump into this piston and push the piston up. So we've raised this mass, right? So a force has moved that mass by some distance. So we've done some expanding, right? Pushing against the things that are from the surrounding that are pushing on you. So if we inflate a balloon, for example, here's a balloon, and we start inflating it so it moves outwards. Oh, my drawing is really terrible today. There's a balloon. So as we start inflating this balloon, it's going to be pushing out on the mass of air, all that air pressure that is pushing down from the atmosphere on the balloon. And so by expanding the balloon, there's work being done because we're pushing this mass of air out of the way. So there's some force that's pushing a mass, the air, some distance, right? Okay. So for expansion and compression work, we sometimes call this pressure volume work, or PV work. We can derive this formula from physics. Now I won't derive that for you, but it comes from this fundamental definition. And so work is going to be equal to minus P, so that's the pressure that's pushing down on our system, times delta V, and delta V is the change in the volume of our system. So if work is done by the system, so let's say the system is having to push this weight up, right? So that system has now lost energy because it's had to do work in the surroundings. So this mass is in the surroundings. And that mass has been lifted up to higher gravitational potential energy. So it has gained energy. So we know if the surroundings have gained energy, the system has to have lost energy. So work has been done by the system on the surroundings in expansion. So anytime we expand, we're going to say that the system does work on the surroundings. And we're going to give that a negative sign. So that's why the minus sign is out in front, because the energy is the system is losing energy, right? And we've already talked about how energy loss gets a negative sign when we're talking about heat. We're going to follow the same convention with work, that if your system is losing energy, well, that's a negative thing, so we're going to make the sign for that negative. So we put this minus sign in front of this formula. So this is an important formula that we can use to calculate the work done by a system through expansion or compression. So if you squeeze down on the system, compression, then we're going to say that the surroundings does work on the system in that case. And in that case, our system would be gaining energy, and so we would give that a positive sign. Now notice that in expansion, delta V for your system, so we'd be starting at a small volume and going when this piston moves up to a larger volume. So V final minus V initial is going to be a number that's greater than 0, right? Because our final volume is bigger than our initial volume. Whereas if we're looking at compression and thinking about delta V for our system, which is still going to be final minus initial, so V final minus V initial. In this case, though, for compression, our final volume would be smaller than it was initially. So we're taking a small number minus a bigger number, and that's going to give us a number that is less than 0, or a negative number. So when you have this negative number, it's going to multiply this negative sign and give us a positive overall sign for work because energy is going in. Similarly, here when the system with expansion, our delta V is positive, and so this negative sign out here gives us the direction for the energy transfer. Okay, so again, work is a way of transferring energy. Okay, so now I've cleared that out a little bit, so let's look at this equation. So here's my first law of thermodynamics. Total energy change is equal to the heat plus the work. Okay? So if we can only do pressure volume work, expansion or compression, and that's true for most chemical systems that we're going to be studying, then we can replace the W right here with this minus P delta V. So this equal sign right here applies only when you can do PV work. If that's the only kind of work you can do, then we can just replace this W with the minus P times delta V. And so the plus times the minus gives us this as our final formula. So this is what we can use to calculate the energy change in chemical systems, which typically only do expansion compression work. So we would know what pressure, need to know what pressure is pushing down on our system and the change in the system's volume. So finally, let's look at this energy flow diagram. So this summarizes what we've just been talking about with our sign convention and the formalism. So here we've got our system. In between the system and the surroundings, there's a boundary that is imaginary, and these would be the surroundings. So if heat is coming into the system from the surroundings, we're going to give that heat, Q, a positive sign, right? So it's positive. So if work is being done on the system, so that would be in compression, then we're going to give that work a positive sign as well. Conversely, if heat is going out of the system, so we're cooling the system off and the surroundings would be warming up, that Q is going to get a negative sign. So remember, heat in is endothermic. Heat out is exothermic. So we're going to give that heat a negative sign. Similarly, if work is done by the system via expansion, the gas expands, we're going to give that work a negative sign because the system is now doing work on the surroundings. Still, it is always true that the total energy change of the system is Q plus W. So there may be some heat in, there may be some work out, there may be work in, there may be heat out. Any combination of these things, we just need to add up the total heat and the total work, and that will give us our total internal energy change for the system. So let's do one practice calculation now that we know a little bit of this. We're going to calculate the work in liters times atmospheres and joules associated with the expansion of a gas in a cylinder from 54 liters to 72 liters at a constant external pressure of 18 atmospheres. And there's a little note here that says 1 liter times atmosphere is equal to 101.32 joules. Okay, so now let's do our problem solving. So we're going to follow this COAST, C-O-A-S-T acronym to kind of go through and solve this problem. So first we need to collect all of our data, so let's think about what the problem is asking and organize it. So what is the problem asking us to do? We're asked to calculate the work. So I'm going to write a little W here because that's our symbol for work and put a question mark. All right, so that's just helping me collect what it is that I'm trying to get is work. We know some of these volumes. So it goes from a volume of 54 liters, so that's going to be our initial volume. Here we go. And our final volume, 2, that's how we know from these two words what's going on, from this where we start, 2. So VF is going to be 72 liters. Okay, the other piece of information that we have is that the pressure, the external pressure, I'm going to write an EX here so that I know that's the external pressure, is equal to 18 ATM. Now, we haven't talked about pressure yet because we haven't done the chapter on gases. That's chapter 6. But ATM is one of the pressure units for gases, and that's called the atmosphere. So ATM stands for atmosphere, and that's a pressure unit. At sea level, the pressure of all the air pushing down on us and everything on the surface is about 1 atmosphere's worth of pressure. If you were to dive under the water, that water pressure would start pushing down on your body, and you can actually feel that in your eardrums as you start going under the water. And it's about 1 extra atmosphere of pressure for every 30 feet in depth that you go, every 10 meters. So if you go down 10 meters in depth, the pressure is going to be about 2 atmospheres down there, and you would definitely be able to feel that on your body and in your ears. So that's just a pressure unit there, and that's our external pressure. So now we're trying to collect other information. Let's see, what else do we know? We know that there's this conversion factor. So 1 liter times atmospheres is equal to 101.32 joules. Now, I've already talked about joule being a unit of energy, so it must be, if this is a unit of energy, that this is a unit of energy over here. So it must be that liters times atmospheres, if these things are equivalent, is a unit that's equivalent to joules. Okay, so this is just mapping out our equivalency between these units. So I can use that as a conversion factor. Oh, hey, that might be helpful up here when I have to calculate the work in joules and liter atmospheres. So maybe there's some connection where I'm going to have to use that. All right, so we're still doing collect and organize, and your book suggests that it's often helpful to help visualize the problem so you can think about what you're trying to get and what you're trying to find. So I'm going to do that. I'm going to visualize the problem by drawing a picture. So here's our picture. So we're imagining that we've got our system here inside our container, and like we saw before, there's a pressure pushing down on the system of 18 atmospheres. Oops, it erased my little arrow. So 18 atmospheres. And then we imagine that this piston is containing this little can of volume to be some initial volume. So this is my 54 liters. And then we're going to imagine that a process happens, so associated with the expansion. So this arrow represents the expansion that's going on. So now I need to draw a different picture. What's different about my picture? Well, the piston is moved up, right? So we've still, because it said a constant external pressure, it's still pushing down with 18 atmospheres, but now we've got a different volume for our system here. It's now 72 liters. All right, so that little picture is just kind of helping me think about what's going on. So now I need to start asking myself, well, what is this question about? So I'm trying to find work. So I'm going to need some sort of principle or equation or something to help me calculate work. We already have done that, right? So in the previous slide we learned an equation, so we go back and look at that. Minus P delta V. So this equation only applies when we're doing expansion or compression work. Oh, but I know that this is an expansion, so I expect this equation to apply. All right, so to use this equation, I would need to know what? So I'm starting to do the analyze part of this problem right now. So with this formula, it tells me that I can calculate work if I know pressure and if I know the change in volume. So do I know the pressure? Well, what is this the pressure of? Well, it's the external pressure. So we're going to imagine that this is the external pressure that's pushing down on our system. So maybe we should write P external right here. This is the external pressure that's pushing down on the system. Then I need to know delta V. Well, what is delta V? Well, that's the change in volume. Oh, hey, I know my initial volume. I know my final volume, so I could calculate that change. So writing this out a little bit differently, it's going to be negative P times the change, which is always final minus initial. So V final minus V initial. Very good. So that's a plan now. I have analyzed my situation. I'm going to use this equation and plug the numbers in. Now, real quickly, I need to think about what units are going to be. So my volumes are in liters. My pressure is in atmospheres, 18 atmospheres. So if I multiply those two things together, I'm going to get units of atmospheres times liters. Okay, well, that was one of the things that I've asked to calculate. the work done in liters atmospheres. Oh, it must be that if you multiply atmospheres times liters, that is the same as liters times atmospheres. But then I also need to calculate that work in joules. Oh, well, I can do that with this conversion factor that's right here. Because I know if I just had 1 liter atmosphere, that would be 101.32 joules. So if I had 2 liter atmospheres or 1.5, I can just multiply to get the number of joules. So now I've got a plan, so I've analyzed. So now it's time to solve. So let's go do that in this next space. Alright, so now we're ready to solve. So work is equal to minus the external pressure, 18 atmospheres, times the volume change. So we have 72 liters minus the volume that we started out with. Remember that initial volume was 54 liters. So we're going to have minus 54 liters. Okay, now we just need to do this calculation. So I'm going to take 72 minus 54, so that's 18, and then we multiply by 18 atmospheres. So let me write that down. So we've got negative 18 atmospheres times a positive, because 72 minus 54 is going to give me a positive number, 18 liters. There's an 18 liter change. And so I multiply those, and I get 324 as my answer. So my answer is going to be negative 324 atmospheres times liters. Alright, so that is one of the 2 answers that I was asked to calculate. Next, I need to calculate that same work in joules. Alright, so I've got negative 324 atmosphere liters, or liter atmospheres. And so here's my conversion factor, and I want to get the answer in joules. So I need liters times atmospheres to cancel out. So let's go look at our conversion factor. What does it say? 1 liter atmosphere is equal to 101.32 joules. Very good. So next to the joule unit, I need to write 101.32 and 1 liter atmosphere. And so this tells me that I just need to multiply negative 324 by 101.32, and that gets me 32,830. Now technically, because my numbers have 3 significant digits in this number, so when I multiplied these 2 together, they each had 2 significant figures, so technically this answer should have 2 significant figures, but I'm going to go ahead and round to 3. So we would move this decimal place 1, 2, 3, 4, and I would write this answer as 3.28 times 10 to the 4th, because I moved it 1, 2, 3, 4 places, joules. There we go. So there's my answer in joules, and it has the negative sign out front. Okay, so let's check and make sure that these numbers make sense. So we would expect the work done in expansion, right, to be negative because the system is doing work on the surroundings. So we do get a negative number here, so that's good. As far as magnitude, well, we don't really know what to expect, but 18 times the volume change, that says what we're supposed to do, and that's what we calculated. Volume change is going to be positive, right, because we're going to a bigger volume, so that all makes sense. Let's think about our conversion here. We know that they're about 100 joules per liter atmosphere, so I should get an answer that's about 324 times 100, and so that ought to be about this number, right? Because if you multiply this number times 100, you would just add 2 zeros after it, so it'd be about 32,400. So it's a little bit bigger than that, so that all makes sense. Very good. So now we've done all the steps in our COAST. We've collected, we've organized, we've analyzed, we've solved it, we've gotten our 2 answers, and we thought about it a little bit to make sure that our answers do in fact make sense.